flat plane mirror produces a virtual image at equal distance on the other side of the mirror. And so certainly that can come in handy. But there are other applications where you might want a curved mirror to focus the light better. And we'll see how that case reduces to this case a little later. All right, so if we have a curved mirror, the basic idea here is that we want parallel beams of light to come into the curved mirror. It might be nice if they could come to a point of focus, like this. Okay, so here's our curved mirror. And so here's our light coming in. Now it's always going to bounce off, so the angle of incidence equals the angle of reflection. Remember, that was our condition for reflection that follows the path of least time. So that's still true here, that at every point along the curved mirror, the normal direction changes. So the angle of incidence is still equal to the angle of reflection, but about a different normal. And so you can set this thing up then with a spherical mirror so that the parallel beams come to a point of focus at the focal point. I should mention here, although these smaller mirrors are usually made spherical because it's way easier to make a spherical mirror, that the ideal curvature is parabolic. And that's what big telescopes are made of, is parabolic surfaces. So spherical mirrors work for small mirrors because you can fit a spherical curvature into a parabola along a small range of values without too much error. But for really big telescopes or big mirrors, you can't get away with that. And so the idea then is that these parallel beams then will be brought to a point of focus at what's called the focal point. And then this distance is called the focal length. And so how could you use something like this? Well, let's say that you have a flashlight and you want a directed beam. Then what you could do is put the light source at the focal point. Same is true with a headlight, but you just have a bigger mirror. And so here would be the light source. Here the light would come out, and it would come out along parallel beams. Because if it comes in along parallel beams to a point of focus, then most things in nature are going to work in reverse. If it starts out from the point of focus, it'll end up as parallel beams. And so that's what you want here, because most of the light from your flashlight bulb is going to be lost in the other direction. You're pointing the flashlight this way, but most of the light is coming, or half of the light at least, coming toward you. And so what you want to do is bounce that light out into a parallel directed beam. And so if you check when you're, next time you change a bulb, you'll see that there's a little curved parabolic, or probably just a spherical mirror, because it's such a small mirror, you can get away with that. It's much cheaper to make. It's spherical mirror, you'll see that you'll be putting that bulb right at the focal point for a curved mirror that has a positive curvature. And so then you'll also have some light that won't bounce, that'll go this way. So this gives you your peripheral vision. So you'll have this focus of the light only in what you're pointing at, but then you'll have some of the light that comes straight out from the bulb that is lower intensity because it's more spread out. That it'll give you a little bit of an idea. So you heard something, and then you saw something, and then quickly you changed the direction of the flashlight so you can see what it is from your peripheral vision that was going on. So that's how it works then with a flashlight and a headlight. Also, if you want to increase the size of the mirror, searchlight will do the same thing. And so in each of these cases, then, the light source is placed at the focal point. And then this results in a parallel directed beam. Okay, so those are some of the main uses then for a curved mirror. But you can also use them in a variety of other applications, and one of them is a telescope. In the case of a telescope, in the case of a telescope, we'll go to the optics section here. We have this kind, oops. Good. We have two different kinds of telescopes. You have what's called a refracting telescope. That's probably the one that you've heard the most about. But there's also a reflecting telescope. So this is an example then of one in which you take the beams of light that are coming in from a distant object. Now those parallel beams of light that come in from a distant object will strike the parabolic mirror in the back of the telescope. And then those will be brought to a point of focus up here. But the thing is, you'd have to be inside the telescope to analyze that light. So you reflect the light outside of the telescope and through a secondary eyepiece. Okay? And so taking parallel beams of light and then analyzing them is the domain of a telescope. And so this is an example of a telescope that does that. The curved mirror is in here. The light comes down like this, and in this case it hits a curved mirror that stretches the focal length out so that the light can come in. And then it goes through a secondary lens here and then to your eyes. Okay, so that's the, and we'll go into more detail about all of that in a little while. But those are the basic uses then for a curved mirror in technology. Are there any questions about that? Okay, so once we've established that then, the next thing we might want to do is take a quick look at how we can form images. different kinds of images that you can form with a curved mirror. And they can be broken up into two categories. So here's our curved mirror. And let's say we're talking about positive curvature for the moment. By positive curvature here, I mean that the light converges. It doesn't diverge. If you have a negative curvature, we'll see that that corresponds to light rays diverging. And so let's say that we want to take a look at a positive mirror here, a big one. And first of all, let's take a look at the kind of reflection that we would see. Now if I bring my hand in close like this, you'll notice that it looks kind of a little bit magnified maybe. And then, but if I bring it out far enough, or if you look at yourself through here, what you're going to see is that are you turned upside down?
Yes.
Can you see that you are? Okay. Turns out that's a real image. It doesn't seem like it because you're turned upside down. Because that'd be real. That's where light is really coming from. And so that will take a little bit of explaining. But let's first of all talk about the virtual image. Because that's kind of like what we did with the mirror before. So if we have a source of light here, I'll call that O for the object. And then we have a place where that light comes together. And we'll put that object inside of the focal length. So here's the focal length. Here's the object distance. Okay, so O and F then are measured with respect to the center of the mirror. Then we're going to want to form an image. Okay, so how do we form the image? Well, we form the image with representative rays that we draw. And we don't just draw any old ray because we're not going to know how any old ray is going to bounce. But there are certain specific rays that we can draw, and we know what they should look like. We're drawing easy representative rays. Okay, so what principles can we work on here that'll help us? Well, one ray that we can always draw is going to come in parallel to the axis and then go through the focal point. Because we know that that's the basic property for our curved mirror. So here's the focal point. Then this distance is the focal length. This is O, that's the light source. Like that. Okay, so the light source then, in the case that we were looking at here, was the pen with my hand. That light source then is in, the focal length is out here somewhere. But it's in here. I know it is because it's making an enlarged upright image, which I know can only happen under those conditions. Then the second ray that we can draw comes in and hits the middle of the mirror so that the angle of incidence equals the angle of reflection. Okay? And we know what the direction of the normal is for this. It's right along the axis. Okay, so that's what makes this easy to draw, is that I can draw it with respect to a well-defined normal. It's the normal at that point. The angle of incidence equals the angle of reflection. And so now, if you're, say, back here, imagine that you've got a big eye that's looking along these two rays. So that big eye is going to extrapolate along these straight line paths to produce a virtual image. Now you know it can't be a real source of light because it's coming from the opposite side of the mirror. So this must be something where your eye's been tricked. It can't be a real physical projection of light. And that's how we narrow this down to being a virtual image. It also looks upright. And it looks enlarged. Looks bigger. Looks magnified. Okay, so those are all things that we're getting from this. Now, there's a handout I'll give you on this, but it's also available in your book. There's a relationship between all of these. This is our mirror equation. 1 over the image distance. So this is what I'll measure here as I. That's the image distance. Plus 1 over O, where O is the object distance. And don't worry about this being a 0. If I need to do 0 in this section, I'll write 0 out. Okay, so unless you see 0 right now, you know it's object distance. 1 over focal, like that. And so in this situation then, what we can say is that O is less than F. So we're inside the focal length. Okay, so looks like here, let's set F equal to 10 centimeters. And let's set O equal to, well, I want to try to keep it somewhat proportional here. So let's set O equal to 7 centimeters. Okay. Then let's find I. Well, 1 over I will be 1 over F minus 1 over O. So find the location of the image. But notice we're doing it with 1 over and not with I plus O equals F. So we don't want to just automatically assume that those are the same thing. You know that from your math classes, that those can't be the same. Okay, so here we have 1 over F, so that's going to be 1 over 10 minus 1 over 7. Okay. And so then I, okay, so this will be the reciprocal of that, 1 over 10 minus 1 over 7. 1 over 10 is going to be a smaller number, so that tells me that it's going to be a negative number. And so that gives me 23.3 with a minus sign on in front of it. So that's how far away we are on this side. Okay, and so that's the location of the image. The fact that it's negative tells us that it's virtual. And then this also tells you it's virtual because the light isn't actually coming to a specific point. This is just the extrapolation of these reflected beams. that this eye is moving along. And if I'd drawn this a little more carefully, it would have gone out a little farther. More like this. You can always fix it up once you've done the math, and you can see, oh yeah, that wasn't very accurate drawing. But I won't ever mark you off for a bad drawing as long as you got the right numbers on it. Okay, and so now looks like I can also get the magnification. The magnification is the image height divided by the object height. But it's also equal to minus I over O. It's the negative of the image distance divided by the object distance. Okay. So in this case then, we're going to have minus a negative 23.3 divided by O, which is 7. So that'll be a little more than 3, plus 3 point something. 3.33. So plus 3.33. So what we've gotten then, from analyzing this equation for the magnification, we could call this equation 2, and this equation for the curved mirror, is that it's 3 times bigger. It's virtual, therefore it's located on the far side of the mirror, and that's a trick of the eye. Are there any questions about that? Yeah.
So M is the mirror, is the
magnification? Right, so that's how much bigger it looks than it actually is. So as I move this in here, there's a certain point where it looks the biggest. Okay, and so we try to find that point then where the magnification would look like it's 3 times bigger than the size of the pen. And that would be what we would physically mean by the magnification. Now it's not going to be as easy to measure because you go, oh, it looks like it's about that big. How are we going to measure that? But you can still do the math.
Is it a negative I only because it's a virtual image?
It's minus a negative. Okay, and so what that's showing us is that it's upright. The sign on the magnification is upright. In other words, it has the same orientation as the object did. So I bring the pen in, and the pen is still right side up when we look at the virtual image through the mirror. Any questions about that? Okay, let me just finish up here. This is kind of a cool little thing. Start passing this around to everyone. But here we've got a couple of curved mirrors. Okay, one of them is just kind of a smooth, regular curvature, and one of them's got a hole in it. Okay, and so what I'm going to do is I'm going to put a source of light at the bottom of this mirror. Then I'm going to put the top on, and then what I'd like you to do is keep this thing in the middle. Just pass this around. What I'm seeing here is what looks like a 3-dimensional representation of that little puffball and that tack and that piece of paper. But my senses are telling me, or at least my sense of touch is telling me, that it's not really there. And so there's a lot more brain space devoted to your sense of sight than your sense of touch. Way more. I think that's one of the main reasons, I believe, why our brains started accelerating their development, its development so rapidly in humans, had to do with visual processing, because it took so much brain space to do it. So, if you have more of your brain devoted to visual, then you might think that you'd believe it more. But when I reach and I touch it, I go, no, it can't really be there, because I didn't touch it. But I'm still seeing it as being there. So why do you suppose that you would trust your sense of touch more than your sense of sight?
Because it can't be faked.
It can't be faked. You've been burned so many times before by visual illusions, right? Even Copperfield, all the magic tricks and stuff. But you'd have to be in a pretty altered state of consciousness to touch something and feel it if it wasn't really there. So that would be unusual. It would probably be a cause for concern. Okay, so see how this works. Here's our source of light in the bottom, and here's the hole in the top. So this source of light is at the focal point of the top mirror. So that means if it's at the focal point of the top mirror, then when it bounces off, it's going to come down in parallel directed beams. Just like
You see it?
with a headlight. Okay, this would be like your headlight, then this would be your parallel directed beams, but there's a hole in the middle. So now the hole is at the focal point of the bottom mirror. Okay, so that means that the parallel beams that come in are going to take a second bounce, and they're going to end up going through this point here. And then what you do is you look from up here. So here's your eye looking along, and what you see are these expanding rays. So is that a real image or a virtual image? It's real because the source of light is actually coming from this location. Even though that's not the original source of light, the light really is coming from where it seems to be coming from after two bounces. And so this is technically a real image, although most people might say, well, it's got to be virtual because it's not really there. But the light is really there. And that's the definition of a real image, is that the light is real. Okay, so I hope everybody gets a chance to see that. How far has it gotten? Great. So be sure to look at that. What I want to do is spend the rest of our time here looking at a couple of problems that are kind of relevant to what we've been discussing. Now, you can have these be due along with the rest of the homework, which would be until Thursday. That these could have some relevance to something that you can see on the quiz on Thursday. So a lot of times, when it seems like there's a problem, going, oh, that's maybe a little too tough. I'll put it in as an in-class activity first. Give it a chance to. Okay, so in the first problem then, we have light that's incident on a water glass interface, and the angle of incidence is equal to half the critical angle. Okay, so that's not this picture. This is a different problem. So it's equal to half the critical angle. The indices of refraction are 1.33 and 1.55 for the glass. So it's going from water to glass. And so the angle that the refractory makes with water then is closest to what? So you're going to have to go through, figure out what the critical angle is, cut that in half, and then do a Snell's law problem. Okay, so it's a two-step problem. In the second one here, we're investigating a certain type of optics fiber that has an index of refraction of 1.27. And we have an incident beam on the flat end of a straight fiber. And so what's the maximum angle of incidence so that we don't have any light escaping? Okay, so in other words, it comes through here, and we don't want any light to come out there or there. So the angle could be coming in like that too. Well, what is the maximum angle such that we get total internal reflection when this thing is bouncing around on the inside? So that's the second problem. Any questions about that? Okay, well, we are available to help, and also